we have a really good family friend who played football up there, and he said that there's always a really big use on the team. We always like stop every use and every day before that they would be sick.
Okay, so
Every single time.
what are our plans? Yeah, predict the future. I can't read. The winter is coming. Since issue of Game of Thrones, this simple phrase starts looking movie. So we are concluding the previous one about the predicting the future propagation of the time, and we are starting the boxes of more than one dimension related to today's lab. And today's lab will be simultaneously next homework. Just complete, make screenshots, and do little verbal explanations. So right now it's still not clear, but after today's meeting and lab, it will be really easy stuff. So we will deal, before we were dealing with box of one dimension, size scale. But if it is more than one, 3 dimensions, you have a different size on each dimension, right? And you provided with the code where you will change the relative lengths of the box. So it will be very confined in one and not very confined in other. So it will be like not rectangular, but not equal size, not a cube, but elongated or squeezed. Okay? And then for each of them, there will be a set of eigenstates, which will be generated by computer rather than by pen and paper. And then you support physical states, which is the subject of today's. And then in a week from now, we may entertain yourself a little pen and paper forward, so that although we do majority of this method, so that we don't. So we do have few realistic models and many concepts. We already actually you guys are finding muscles, mathematical muscles, for being able to consider more complicated models. So we are playing this little toys in order to do something more serious. And by now you have time dimensional Heisenberg practice on free space, and for box we also touched basic metrics, and today there will be concept of density states. Anyone except Ben knows what is density of states? Okay, then it is good. You will or maybe we will ask them. So leftovers. We did practice the probability distribution of particles in the box for the superpositional initial state. And we decided to reconstruct it by pen and papers as much as possible. We agree that the probability distribution is composed of several, actually 4 terms, each of which contains factors, time-dependent factor and spatial factor. The time-dependent factors are really simple, and the spatial factors look like trigonometric functions that we need to process. We decided to process it only at a specific time when the effective propagates quarter period and half period, assuming that in the rest it will be repeating each. Then we stopped at these expressions for the 3 instances, and then we decided to put sine squared by x over L out of bracket for each of them, which was not wrong, but it is a little more efficient to look at from bird's eye, birds not mid. When I was talking, one of my participants thought that bird's eye, it is an insulting expression. Is it a person with bird's eye stupid as a bird? No. Bird's eye meaning like from distance, from by flying and seeing many things globally. So if you look globally, we can identify the full square. Square of sine pi x, square of 2 sine pi x. And here is the same factors. Double sine and single sine and factors in front of them. You see? I forgotten about it last time. And was not able to identify it. And if you look on the lower line, this a square, single sine, b square of this sine of double argument, and then product of them with sine minus. So if we decide to identify full square, it will be a plus b and a minus b squared, right? Where a and b are sine pi x and sine 2 pi x. And after making this step, so we can open the sine of double argument because the sine of single argument, right? Sine of 2 alpha is 2 sine alpha sine alpha. And then we see that still there is a common factor that you can put out of bracket in each of terms. So sine squared pi x over L goes out of bracket in each at each instant of time. And then the rest looks like 1 plus cosine of single argument, 4 cosine single argument, and 1 minus cosine of single argument. Then we may want to plot this stuff. So I will quickly go over details for only instant of first instant of time corresponding to time equals 0, and then the rest follows the pattern. So we can focus first on the cosine of single argument, and as we propagate, as we inspect positions from left to right of the box, when x equals L or x divided by L equals 1, it makes the half oscillation. And since we multiply by 2, it changes from plus 2 to minus 2. Right? Yep. So do not look for deep scientific sense. There will be like 4 slides, only simple math. Just going to begin. When you add 1, it means you shift everything up. And then this stuff that is shifted up intersects the axis somewhere to the right from the center of the box. Okay? And here we need to take square. So plus, minus 0. And when we take square, plus remains plus and minus becomes positive, right? So there, upon taking square of this expression, it will be somewhat higher at the left, somewhat lower on the right, but positive, and it will touch the 0. And the rest is multiplied by sine square, which does half of a period, and since it is square, it will be always positive. Sine square goes from 0 to half period, and instead of bumping at 45 degrees to the edges, it goes a little smoother because square of a small number is even smaller number. And after we multiply this green dots by black line, it becomes 0 left edge plus in between, again 0 at some point shifted from the center, then again positive, and then again 0. Right? So it is a snapshot of our wave packet of our balancing probability distribution for the superpositional state.
It's shifted because of the 1 plus the 1 and the additive.
Yep. I'm not intending to include problems like this in homework, but I want to hear if you will be able to in principle.
So the blue line is the final.
Yes, it's
Actually,
just plot of this function.
Okay.
Like if we do have like graphical calculators or computers at our disposal, we can just plot the function. But sometimes if it is more complicated than science and we do not have immediate shape of the function, you can quickly sketch how it goes. Okay. Anyone would have problems with the same? No. Okay. And then in the middle, the counts will be equal to the left, right? And on in the half period, it will be shifted to the right. And any snapshots, time snapshots in between will be interpolation between these shapes. So when we have all of them together, we are we will have all of them together. We have this wave packet that you're probably tired of, the bounces, force and back. Okay. We will see similar behavior of in more than one systems later in the class. So it is just simplest possible model where we can obtain it by pen and paper and by computation. So done with the previous meeting, and here is how the main feedback from your lab work and simultaneously next homework should look like. So, do you see any connection between this figure?
Those 2 humps.
Okay, perfect. But what were the axes in the previous humps?
Position and expectation value.
Yeah, probability distribution. And what are the axes here?
Energy intensity of states.
Okay. So, can you project and see any connection? I'm asking everyone except Ben because I'm aware of his practice for researching. It will be someone of you told it will be unfair benefit if I would ask him. Yes.
That's more energy. So is that anything with like solids and gas? Is it like heat and
Yes, yes. So the goal with the density of states concept is to enable analysis of energies of states in any quantum system, not only in quantum boxes. In case there are so many of those. In previous section, we looked only on two states, and we already got tired. But in you know that in Schrödinger equation there is infinite number of solutions. There is so many energies, and if they are spaced by very little energy offsets, there are so many of those. A human would be tired to look on the numbers or even on the offsets as levels. So the density of states is a concept that summarizes energies into individual. This summarizes energies. So if there are so many levels and they are offset by little values, one can develop the distribution of energy. So at some intervals of energies, the eigenstates are more dense. At another, they are more sparse. And this signature, which values of energies these energies are more dense and sparse, are very specific. They're specific for each quantum system. And by looking at density of states, which can be either computed or measured, there are experimental tools that measure them, such as scanning tunneling and proton. One can, by the signature, construct what was the system. So it's similar to spectroscopy. And those who are practicing computational chemistry, it is a major thing to compute, probably the simplest thing to compute. If you were looking for summary, we're done. The rest are just details. So, who is this little stairwell walker? Perfect student. Perfect. Why this tortured student is walking over stairs, and what are the stairs here? Huh?
Kind of endless stairs.
Endless stairs, yes.
Don't each stair step represent a new energy level?
Yes. What is the x-axis?
Energy levels, right?
Well, now I will tell the phrase that you freeze everyone. So, as you remember from previous lectures, the energy of level number n is square of the number of levels times some constant, right? We didn't lose the constant. I see in your eyes. So you do remember. So if we can divide, so it is this constant times number of levels squared. So if you divide left and right by E naught, it will be E n divided by E naught, right? So for our particle in the box, it will be n squared, right? The larger the number of state, the higher the energy, and the energy grows quicker as n squared. Right? It's true. Now, what is y-axis? So this would correspond first the ground state, first excited, second excited, 1, 4, 9, 5, right? Make sense? It's just progression of n squared for natural numbers. But what would be the y-axis? What will be the height of the stairs for this torture student?
Energy required to get to those states.
No. So the height of each step is 1. And each time we go from one energy level up, it changes by 1. So we were in ground, it is 0. We are in first excited, it is 1. We are in second excited, it is 2. We are in third excited, it is 3. In fourth excited, it is 4. So you can tell it is either just index of the eigenstate, or we can think as it is number of energy states behind us. So if this walker jumps to third excited state, he's on the third level. There are 3 states behind him. And look back. Let's say, I'm already so high. I passed 3 grades. 3 energy levels are behind me. Make sense? So we can call this as number of states behind you as function of energy. I'm so energetic. I have this much energy. And so many states are behind me. Do not mix with energy units. It's just abstract energy for quantum theory. Okay? So you do have a concept of NOS, number of states behind you. I didn't type it here. No, I did. NOS. Good. So we're already done. We need DOS, and here we have NOS. So we just need to change the first letter. Right? What is a derivative of a step function? Well, first, you may have been exposed to this in one of the math classes. Second, it is already written on the board.
Isn't it that green box equation?
Well, green box equation is just definition of density of states. It's derivative of numbers. So let me jump back one slide to this tube. So if it is a number of states, as we progress along the energy, we can take derivative of the stairs. Yeah, not crazy. It's not stairs, wooden stairs. It's just abstraction. So when we are between steps, derivative is 0. But when we abruptly jump up, derivative is discontinuous, so it is infinity. Right? Make sense? So derivative of a step is infinity. But it is infinity only in narrow, not in vicinity, only exactly at this point. So it is definition of delta function. Derivative of a step. Symbolized by letter Greek delta. So if here are the steps, and here we take derivative, dn over d epsilon. Derivative of steps over energy. Each time we are jumping up, it goes to infinity. Between it is 0. Infinity, 0. Infinity, 0. So the peaks appear at such energies where we have actual eigenstate. Okay? So for one step, it is just delta function of energy, and this is of energy as a continuous variable. And this E sub n is fixed known energy of quantum state. And since we have so many quantum states, we need to add together all of them. So this is a more boring, rigorous mathematical definition. But if we are simple guys who look onto the nature of phenomena, you will learn very soon, or life will teach us, that there are no absolutely precise values. Not because of the restrictions of the theory, just whenever you do experiment, there are some factors like shaking and soft hands, an interaction with another degrees of freedom that will make the error bar, right? For anything you measure. And sometimes this error bar, it is not bad, it is just influence of other degrees of freedom. So therefore, the energies of each level in practice will be not exactly at this point, but there will be some error bar. Therefore, instead of true delta function, one typically adds a little shape so that it is not infinity, but a little wider than zero. So for this true delta function, the width is 0, and for the fake delta function, approximated delta function, one can assign a little width. So this is the stairs, this is delta functions. So for the going from nothing to first state, E minus E sub 0. For first excited, energy is 4 times bigger than ground energies, offset as much. For the third state, it is 9 times. And everywhere we get a little peak. Right? So formally, this is already density of states, which is not practical and not needed if we have a handful, small number of states. It will be needed, it will make sense only if you go into the limit of denser states. Any questions right now? I do not want to go lose the content.
What is the E? So you have E minus E subscript n. What is E? Is that the energy of the system at that time?
Not time.
Oh.
From quantum point of view, any molecule or piece of material or any system is just set of eigenstate energy levels, which do exist no matter if we know about them or do not know, if we use them or do not use. So it's the complete range of eigenstates. And we do want to develop a tool to look on all of them at once. So those are eigenenergies. This is E sub right here. E sub n equals E0 n squared. We did a couple of slides before. And this E naught will be like pi square h bar square divided by L square, or L is size of the box, right? Make sense? So this set of sharp teeth is density of states, but it is not useful for sparse states. When states become not sparse, in which we do not have experience with other systems, 4 particles in the box. What does control sparsity of energy levels? How they sparse or dense? The value of this E naught. E naught is proportional 1 over L squared, right? So what should we do with the size of the box to make the levels denser? To increase or decrease the size of the box?
Decrease.
So if you decrease size of the box, so if this L becomes 1, approach 0, then 1 over 0 will be infinity, right? So the offset will increase. It will be quantum confinement. But if you set up this L equals to infinity, or very large number, 1 over 100, 1 over 1000, this E naught will become very small, right? And it will be the same pattern of energies going offset, like 1, 4, 9, 16, but the absolute value offset between them will shrink. So for larger box, offsets shrink, and levels become denser. Larger box, offsets shrink. States denser. I should show this slide before you. It doesn't touch our scientific intuition, but it's just standard mathematical notations about applying derivative to steps. So theta function, the step, will be 0 before critical point and 1 after critical point. You just define it with brackets. The delta function before critical point and after critical point are 0, and at the critical point it is infinity. We also define it with cases, with bracket. And the properties of these two functions, step function and delta function. Step function is heaviside. It was designed for this electrical engineering signals. So that if you integrate delta function, which means area under this infinity high spike, it will be equal 1. So integral of step function equals, or integral of delta function equals step function, and derivative of step function equals delta function. Okay?
Can you say that one more time? So just the very last part where you said the derivative of something equals something, and then the integral of something equals something else. So I can get that down in my notes.
Derivative of step function equals delta function, spike. Derivative of step equals spike. Integral of a spike, integral of a delta function, equals step function.
Oh.
Okay?
Okay.
So here is our density of states, which is just derivative of number of states over energy. And delta function can be, we do not know too many functions. We have only one known function that looks like a spike. It is Gaussian shape. So if you set the width of Gaussian shape, it will be approximately equal to delta function. And the argument of delta function will be just E naught times n squared, or n is number of the state. Okay, so I will pretend that I'm a little computer and do things that actually will be done by MATLAB this night. So suppose that I do have energies at E naught, 4 E naught, 9 E naught, and our density of states is just spike at each energy where we have eigenstate. Now, I'm going to practice an increase of the width of this delta function. I'm missing the pleasure to redrawing it because I hope if it will not work, I will redraw it back once again. So when they are offset far enough, it will be just fat spikes apart from each other. But if they are close to each other, or if the width of each spike is bigger than offset between them, then the peaks become not resolved. They will merge together as one bigger peak of higher intensity, right? So if we increase the width to the crazy size, then originally we had peak at 1, 4, 9, 16, 25. So when we had 1 and 4, several peaks, like first from 1 and 4 and maybe from 9 will add up together. So it will be higher density. When we will have this one, it will be a little less because the neighbors do not contribute much to the heights of the peak. And as we go away from 0, the offset between states becomes bigger, and the density of states, the result of the summation, becomes lower. So when states are dense, this density of states is higher. When they're sparse, it is lower. Okay. You don't want me to plot it. Once again, it's fine. So a little math. Suppose you have an axis, one axis, it's a different plot, where x is number of state and y is energy, right? So as long as, and we are considering the limit of this E naught is small. So, small. As far as, so small that instead of discrete energies, we just write it as continuous function. So we can tell that energy as function of number of state is just a quadratic function, right? No objections. Now, what is the number of energy as number of state as function of energy? We just solve this equation for n, right? We divide left and right by E naught and take square root. And how does it look graphically? What does it mean to inverse a function in a graphical sense? Yes, yeah, perfect, flip the axis. So if you had exponential, the inverse function logarithm is looked the same way, but it is a mirror reflection along y equal x, right? So if we had the energy as function of n as quadratic, then the number as, if you flip the axis, number as function of energy will be square root. Excellent, we have generous 4 minutes. It should be sufficient. So here is your favorite function that we just derived from the previous slide. No one was objecting. Number of states is square root of energy. So it is the stairs we started from with a tortured student climbing across the stairs. But there it was discrete limit when offsets of energies were large. But if we are coming to the limit of very large size of the box, very small offset between energies, continuous limit, then number of states as function of energy. So the length of each stair of each step will be longer and longer. So first it goes up sharply and then it goes not so sharp, right? And now the main equation, main derivation of today's meeting. If you are sleeping, wake up. There will be something useful. So definition, density of states is derivative of number of states over energy. Number of states is square root of energy. So applying the definition, we need to take derivative of this square root. So we need to take derivative of this number of states. The factor 1 over square root of E naught goes outside of derivative because it doesn't change anything. And then square root of derivative of square root is derivative of E to the power 1/2. What will be the, well, the answer is already written, but what is the derivative of x to the power n? How does derivative change the power?
N minus 1.
Yes. So if n was equal to 1/2, what will be n minus 1?
Negative 1/2.
Yes, negative 1/2. So derivative will be e to the power minus 1/2. Right? Nothing cheesy. Pure math. Literally direct. So it will be density of states for particle in the box, for one-dimensional box. Energy to the power minus 1/2. How do we draw this function? How does it look like?
But the one that's need, right?
Well, the square root of energy grows slowly. Right? How does function 1 over x or 1 over e looks like? It's a high pike near 0, and then it drops down. But if our argument is not x, but square root of x, it will be the same trend, but will drop a little slower. So 1 over x will be big drop, and 1 over square root of x will be slow drop. That's it. I don't know what. So there are so-called scanning tunneling microscopy. When one puts a sample of molecular material on a metal substrate and then puts a very tiny gold needle on the top, and then scans voltage and measures current. So if the offset of voltage matches eigenstates of the sample, the current will be higher. If it is not, it will be lower. And therefore, by it's one can reconstruct density of states. So when we will be doing lab at night, we will see this slowly dropping stuff. And there will be slowly drawing stuff again and again because of another degrees of freedom. But this shape is mathematically proven. Done. Hope you're not very tired and hope you have energy for the lab.
I'm not good. I'm sorry.